No, well, we should record the joke, definitely. And so our next presenters are Kevin Wilson, and he'll be ably supported by Jake Bowers. Kevin is at Brown, probably remotely at the moment, as he's physically now in Toronto. So he is one of us, and Jake is, of course, all over the place, but also at University of Illinois. And they've put together the policy lab, and just putting together a huge amount of resources and really cool analysis. So I'll put the link in the chat for folks that are unfamiliar with that, but going to give us some advice about reproducible field experiments. So thank you very much, Kevin.
And thank you, Rohan, for the invitation. It's been really great to see all the different talks that have been happening. In fact, many things that I was going to say have been said by others, so we'll probably speed through that part of the talk today. It's great to find like-minded people. So as Rohan said, I'm Kevin. Jake is the other person who's un-camera muted, whose camera is on. And we are both of the Policy Lab. And 6 tips for reproducible field experiments is the theme. But really, honestly, like reproducible field experiments is really successful field experiments, in my opinion. And so you'll see that I will slip between this language, things that, I will say like, don't do this because you will fail miserably. And really, they're kind of one and the same, as in my opinion. And this talk could be subtitled, Don't Do What I Did, because these are all hard fought and hard learned lessons. So please learn from my mistakes. So the story of a field experiment, right? What is a field experiment? Some bright young lad is like, what if we did something, right? We're going to make some change in a policy. We're going to try some intervention somewhere. Surely this is going to work, right? So you go, you gather up all your people, you get the government involved, you get everybody in a room, all your stakeholders, you line up your funding and everything else, you're pointing at screens, trying to make people convinced that you should do things. And finally, you go to the big boss, and the big boss says, go forth and experiment. You got your sign off, right? All this work kind of gone into this, and you release your experiment into the field, and and all things are wonderful. And then many months pass, and you go to look at your results, and this is what you find, right? This is ostensibly field experiments. Like the whole idea of a field experiment is that that the data analysis portion should be utterly trivial, right? Like there's an independent variable and a dependent variable, and you run a t-test, right? But so many times in field experiments, you get to the end and you're like, oh no, how many other regressions do I need to run to make sure that I didn't screw things up totally? So in this talk, basically, I'm going to give you 6 tips for avoiding this fate, things that I wish I had done in the past in order to try to make it so that the ideal of getting to a single t-test in the end is actually what you end up doing, as opposed to needing to do a lot of sort of reproducibility work. And a lot of the theme here, just to say again, is that, I think Lars mentioned yesterday something along the lines of at some point I've got to trust your data. And a lot of the theme here is about, well, how can we improve the trust in that data that we as researchers can believe our partners, especially in field experiment land, where we're not like Kevin Wilson, and not like the government of Ontario, who's going to be implementing this thing, right? Like it's like there's somebody on the other side who's going to have some say. So these are my top 6 tips. So 1, and randomize the deterministic data. And throughout this, we'll explain what these mean. 2, randomize with code and get a copy. 3, write your SQL before an experiment begins. 4, for rolling experiments, continually run that SQL. 5, plan for a multilingual environment, code. And 6, plan for a multilingual environment, data. And really 5 and 6 is where a lot of this conference has been focused on. And especially I really like John's talk for the previous one to this, who is doing a lot of talking about like how code and how to set up your coding environments and things like this to plan for this kind of thing. So I'm mostly going to leave that to like CF the rest of this conference. But it is still one of my top 6 tips. So focusing mostly on the first 4. Okay, so you came to the tips. So what are the tips? So tip 1, randomize the deterministic data. So as we said, there's really two parts to a field experiment. Tips 1 and 2 are about the independent variable. Tips 3 and 4 are about the dependent variable. So this is the independent variable side, which is your randomization, your treatment variable. My tip is randomize with deterministic data, which is, what does that mean? Well, if you think about a field experiment, a lot of people touch your random assignments, right? So to give an example, some colleagues of mine at the lab at DC, once upon a time, were trying to evaluate whether or not the introduction of body-worn cameras to the police force would actually end up having an effect on how citizens and police interacted with each other. And so they took the whole roster of police officers in the District of Columbia, and they assigned some of them to get a camera and some of them not to get a camera. They shipped that list over to the chief of staff of the DC Police Department, and they said, please do this. A week later, the chief of staff from the DC Police Department gave them a panicked call and said, I seem to have given everybody labeled with a C a camera, but I think you told me that meant control. And they said, yes, so you did the opposite? And yes, in fact, I did the opposite of what you told me to do. And conveniently in that case, it was actually a great lesson in randomization because it was a 50-50 split, so it didn't matter. So they made a note in their log and said, like, okay, right, just to have to remember to flip that at the end. But this is a classic example of you don't control the person who's actually doing the treatment assignment, usually in a field experiment. Somebody else is going to assign somebody to do something. You're going to tell them to do it. They may not do it. And so an important thing is that if you can, you want to have as few steps as possible where things can break, or you can lose something, or that you can disagree. And so typically when you're doing a field experiment, every one of your subjects is going to end up with a unique ID of some kind. And if you could transform that unique ID into a random assignment, that would be amazing, because all you need then is to recover your random assignment is the unique ID. And you can just do that over and over and over again. If you lose the Excel file, who cares, right? You just run it again, life's great, right? So there is, it turns out, a way to do this. And this is through the use of pseudo-random hashes, which come from computer science. So essentially, if you just hash that ID and then use, say, if it's even, do one thing, if it's odd, do another. If it's, if it's in an order, that's the type of thing that's useful here. So as an example, here's some pseudocode. I promise there's not too much code in this talk, but just to give an example of what this looked like in practice. So you've got some data, and so like for each row in the data, set the sort order to be a hash of the unique ID, sort the data by the sort order, and then assign the first p times n to treatment and assign everybody else to control. And that will give you a proportion p assigned to treatment and a proportion 1 minus p assigned to control. Very simple, but it's much more reproducible than say, sample or complete array or things like this inside of R. So that's tip 1. Tip 2 is on the next note, which is that, again, randomization is like one of the 2 key components of your field experiment, right? Independent variable is the randomization. If you're not doing that randomization and you don't understand what happened during that randomization, you don't really understand what happened in your experiment. And so a very common situation is that you'll be embedding these field experiments inside of code that other people are running, or inside of systems that other people are running. You should get a copy of that code, because many, many things can go wrong. And it's really good to test that code, to store it with, and you should store it with your analysis code. So you can always go back later and say, well, how did we do that randomization? Like, I'm seeing all sorts of weird things in the end. Like, what did we actually do? Right? And it also helps in the reproducible side for future people to say, what did you do? Right? They can actually look at the code and say, that's what they did. I understand, right? As opposed to, we randomly assigned people. So you should really get a copy of that code, store it with your analysis code, write tests for it, try it on historical data. And honestly, like, if you can hover over somebody while they run the code, you should do that too. Screen sharing, like going to wherever they are, whatever that is, make sure that they're actually running it correctly, because I've also had that go wrong. And I'll give you a bit of a story time here. So first off, you might be asking, what's a good randomizer? This is a little bit of a prelude. Good randomizers are hard to define, but basically they should eat typical data, whatever your typical data looks like. And when you run it through your randomizer, they should give you something that like looks uniform. That's generally what you should be going for, right? Like there's a lot of asterisks on here. read Knuth if you really want to know the details, but really call a mathematician if you ever go down this path, because lesson number like -2 is never write your own randomizer. To wit, we had a partner that we were working with, a small state labor department. You might be able to guess the state by the location of my university. And we called them and they wanted to do a field experiment on a new program that they were running. And we were like, that's awesome. Okay, so how many people are you getting per week? How are you going to do random assignment? And they're like, oh, we've done random assignment before. We have a hash function that we use to assign people to treatment and control. And I was like, oh my goodness, they're already doing tip 1. This is amazing. And so I asked, so it's like MD5, SHA-256, like what's that hash function you're using? And it said, oh, Bob wrote it 20 years ago. And I'm just like hearing taking deep breaths of like, can we please see the hash function Bob wrote 20 years ago? I was like, yeah, sure. So off my colleague Ed went down to the office where they were, and they printed out a copy of their hash function. They in fact annotated it by hand. So all of these marks are from the pen from Steve describing to us exactly how this hash function works. His description of the numbers on the left-hand side were those are the magic numbers. And his description of seed num was like, that's where the social security number goes, right? And LRAND whole, big circled on the right, that's the output. He's like, well, what goes on between seeds? It's like, that's what Bob did, right? And so this was their randomizer, right? They were going to do exactly tip 1. They're going to take the first 100 people in this order and assign them to treatment, and everybody else got assigned to control, right? Amazing. But what is this thing doing? Is this a good randomizer? It looks too short to be a good randomizer. And so step 1 was, if you can't tell, this is in COBOL. I don't read COBOL. So step 1 was to rewrite it in Python, which is a language I actually kind of understand. And so we had a whole process where we rewrote it. We understood fixed point arithmetic, got out the decimal package. We did some back and forth about, is this a good and faithful translation of this program? We sent test cases between us and everything else. And we kind of realized that 2147483647 is actually 2 to the 31st minus 1, which is the largest Mersenne prime that's less than 32 bits. So it's like, this is a Mersenne twister sort of thing, but it's only 1 round. If you know what randomizers are, that makes sense to you. If you don't, this is why you call a mathematician to write your randomizers for you. So we realized it was kind of a Mersenne twister. We're like, well, let's see what it does, right? Maybe it's okay. So we took a uniform collection of like fake social security numbers. Social security numbers in the United States run from 0 to 1 billion, basically. And we looked at the output. I don't know, this looks pretty good, right? Like, kind of looks like white noise. That's what you expect, right? Like, uniform inputs leads to uniform, scattered outputs. Except, remember, the key is typical data that you get, not uniform data that you get. And an important fact about social security numbers in the United States is that social security numbers are not randomly assigned. Well, they are after like 2011. But a very key fact but you're probably not doing these field experiments on children. So so most of your sample will not have a randomly assigned social security number. And in particular, they used to be assigned more or less sequentially by hospital, right? So like my father and my sister's social security numbers share the same first 4 digits because they were born in the same hospital 34 years apart. Mine start with the different digits because I was born in a different hospital. So, this is actually observed, right? So if you're in a small state with only 2 or 3 OBGYN clinics, turns out that social security number is going to be pretty correlated with age. So this is not a good thing to be doing if, for instance, if you run sequential numbers, social security numbers through your algorithm, and it gives you back sequential numbers. So this is an example of a bad randomization algorithm, not too bad, right? Like on uniform, it gives you uniform, but that's not a typical use case. So testing out these randomizers is quite important. And as I say, like lesson number 1 should be never write your own randomizer. But if you must, do call a mathematician, conveniently, that is me, and ask them to ask questions of it to make sure that it's running. We eventually came up with a good enough randomizer involving like reversing some digits and adding in some time and things like this. It was good enough for our purposes, but you really need to know what's happening because again, this is like one of the 2, like there's only 2 things you need out of a field experiment, and this is one of them. And you really want this one to be right. So your best bets for copying for tip 2 are don't write your own hash function. If you must, please consult a mathematician. 2, do try running your randomizer on historical data and check for assignment balance using a tool like XBalance, to shout out Jake over here. That will help you understand if you're actually getting balance. And if you'd like some examples of how to do this, you can see this GitHub repo with our pre-analysis plan and everything else for this particular experiment that's currently in the field. Okay, so we talked about the inputs, right? We talked about the ID, the independent variable. So now we're going to transition to the dependent variable. Okay, so tip 3, write any SQL before the experiment begins. So what do I mean by SQL? I really mean any code which pulls out outcome data, which almost certainly will be SQL if you're working with somebody who's collecting data using a database. Because ultimately this code defines your metrics, right? And if you don't know what the SQL does, you really don't know what your metrics are, right? Like, how did you compute that somebody actually went to something? What were the cutoffs? What were the limits? How was that actually feeding all in? And in particular, because that SQL is the code that runs and actually does something, that's literally the definition. And so if you write this beforehand, you make sure that everybody agrees what the variables mean, right? In fact, an important example of this is that Jake and I actually just had a paper come out in Nature, or I guess it's pending in Nature in a few weeks. And we had in halfway through the experiment, we realized that our partner had totally misinterpreted what we asked for, and that they were giving us the wrong outcome data, which was quite devastating to us briefly, but we fixed it. But this was an example of like, please do write your SQL ahead of time. We were running very fast on that one, and so perhaps we're a little fast and loose and should not have been. And to say that particular example was a common example of something that shows up a lot for like why this is important, because oftentimes in writing your SQL ahead of time, you end up in this world where there's this difference between intentions and actions, right? And often where you are able to randomize in a field experiment is on the intention side. You're often working with the people who control the web forms or the advertisements or the sign up solution, the person who can send out text messages. So what they can usually measure is something like clicks on an ad or like views of a page or like walks in the door. But what they can't measure is like, did somebody actually buy the widget? Did somebody actually get the vaccine? Did somebody go to an interview, right? And that's usually housed somewhere else. And by forcing yourself to write the SQL ahead of time, you will probably very quickly find out that it's not Judy who you're talking to who owns that data. It's Janet over there. And they'll be like, oh, well, you got to talk to Janet for that. And you might find that Janet doesn't even collect that data. And so, before, actually running your field experiment, if you intend to measure action, writing that SQL ahead of time is a good exercise to make sure that you actually can measure the things you set out to measure. And problem 4 is that, you should really run this SQL continually once it's written, because the problem here is that whatever you think about the field a priori is almost certainly not true. And you will find everything that you do to try to mitigate stuff will in fact blow up in your face at some point in time. Are you actually capturing that data? Janet said that she captures XYZ data, but does she actually? Is it good data, right? Is the randomization actually occurring? Sometimes they forget to flip the button. True stories. And is there an extreme contamination that can be remedied, right? Are you accidentally getting too many people in your randomization scheme, and are you off balance? Are you getting too few? Are there things that you can do to correct your experiment early on so that you don't get to the end, wasted $1 million of time and resources, and then been like, I don't know what I can do here, right? So the key here is really just basic stuff, right? Monitor your experiment. So you should be having things like regular meetings with your co-experimenters or your partners. But really, on the tech side, those meetings are usually with the project managers or the program officers. You really want to have the regular meeting with your technical staff who's actually pulling the data for you. Basically looks like them giving you the data and running that code on the regular. So if you've written that code from tip 3 ahead of time, you can just ask Janet to run it every few weeks to give you a copy of the output. And now you can actually monitor your experiment quantitatively, not just kind of like the program officer said it's all working, which is an important place to go. And of course, what does that look like in practice? Well, many people at this conference have given really great examples of like how to build pipelines, SnakeMake, John's talked previously. Maybe you involve some Airflow or some Pandera or Great Expectations or these tools. There are many, many tools to make this happen. But really, even if it just involves you running some scripts on the output that your partner sends you in an email every once in a while, like this will solve 90% of your issues. And it's even better if you can get your intern to do it, because that forces you to explain it to your intern and actually gives you a check on making sure that you actually are checking things. This is just basically, the key thing here is that making sure to run that code continually, because again, there are two things that come out of a field experiment: the treatment assignment and the outcome. And if you aren't going to get good outcomes, then your experiment's not going to go anywhere. So just some top things to check for. Data types should be as expected. Schema should be as expected. You're actually getting the data you're expecting. Covariate balance. Your treatment assignments are behaving approximately as you expect. Is there a lot of missingness on the outcome variable? If you're not getting the outcome variable, you're not getting an experiment. And any other sort of assumptions you made in your analysis plan, right? Like, are this right number of people coming in? Are they coming from the right places? Making sure that your analysis plan actually will be able to be executed on. There's a great, if you Google Peter Baumgartner testing for data science, he wrote this great blog post a few months ago that really goes into some examples of how you can actually do this in practice. And as I say, there's also many, this entire conference has been filled with people describing how you can do this in practice. So please see the previous YouTube videos about this as well. Okay, finally, I said I'm not going to talk too much about the latter things, but just to emphasize, when you're doing field experiments, you're stuck in a multilingual environment. You really don't, both like your team is often coming from lots of places, right? You might have, Jake is an old school R person who gets like pulled in on a contract to do something. I'm a Python person always, and I hate when people make me work in R. Or like Shauna here is a partner of ours who like always uses Stata and will just not learn anything else. And it's totally reasonable for her to say that. And so even on your project team, it's hard to control that you're going to have one single language you work in, and your partners are a black box, right? There might be some SAS back there. There might be some SQL. There might be some COBOL. God knows what's going on over there. And so you really are kind of stuck, even if you can get your team to agree, that your partners are not going to agree with you. And so you're stuck in a multilingual environment. And so planning for that is very important. And really that mostly amounts to planning. And so if you want, here is our version of this. Again, there are many examples. So you can go to the Policy Labs GitHub page. It should be the top repo right there right now, just multilingual repo outline. Just giving an example of how we go about, thinking about how to organize our work in light of multiple languages that are coming in. You'll also find at github.com/thepolicylab several other projects that we've come out with recently, specifically, showing examples of how we do that work. So it's not perfectly organized. I was very jealous of John and being able to like do that. I really like that talk, and there are other ways of organizing this, but this is this is our version. And similarly, just on the same note, your data is your data. You're also going to be planning for data to come from lots of different places, right? Surveys will come to you in .save files. People want to give you CSVs or TSVs or zipped up God knows what. For whatever reason, old school labor departments really love fixed width files, having to do with like COBOL really likes fixed width. So you're just going to have to like accept that your data is going to come in all sorts of ways, all sorts of schema, and you just really have to be prepared for that. And again, that's mostly in planning. But I will leave you with one tip that I haven't heard too much of at this conference, which is simply, at least on your internal team, I really highly recommend that you trade files between each other using Parquet as opposed to using CSVs, because it will maintain your data schema. And so when like read underscore CSV decides it wants to convert numbers to floats, and pd.read read CSV decides it wants to convert them to ints, that won't happen, right? You'll all use the same schema. And it's very easy to do. Basically, every time you see the word CSV in your language, you just change it to Parquet. And this will, I swear, this will like make your life much, much better as you're trading files between each other. So that's my one tip here, other than just being prepared for it. And as I say, seeing the rest of the talks of this. So just to summarize, top 6 tips. 1, randomize with deterministic data so you don't lose track of who's assigned to which condition. 2, randomize with code and get a copy so you don't lose track of who's assigned to which condition. 3, write your SQL before the experiment begins so you measure what you want to / need to measure. 4, for rolling experiments, continually run your SQL to receive alerts when something is going wrong ASAP. And 5, plan for multilingual and collaborative code environments. And 6, plan for multilingual and collaborative data environments. So those are the tips. That's it. That's the talk. Thank you for the time. This is the email address if you have any questions. And I'm also obviously happy to take some questions now.
Thanks very much, Kevin. Very annoyingly smart and funny. I'll just ask Jake, do you have anything to add? And while you're thinking about that, I'll ask Kevin, do you have any, are there books and resources that you'd recommend on this? And if folks have other questions, please raise your hand and then I'll call on you. But Jake, do you have anything to add?
I think the main thing to add is that I think that we came up with these tips because we actually made all of these errors. And even though I assign the Gerber and Green field experiments book to my graduate students constantly, and there's even a chapter there about planning experiments, it's hard to imagine that you might not know who's in the control group until you don't know who's in the control group. And so we're trying to alert people to have some more fear in their hearts, eat more donuts so that to overcome the fear. But, still, there isn't sadly like a nice book about this. And in fact, this morning, I ran into a situation where I didn't know who was in the control group, but we couldn't include the story because it was this morning. Kevin.
Yeah, and as Jake said, on the field experiment portion, I've actually not seen very many good resources on this specifically. There's folks, and in fact, Jake, as we were writing these slides, Jake was like, we should write this down. All of the code associated with all of their field experiments they do, and they've existed longer than the Policy Lab has. So you can look at the Policy Lab's GitHub for some actual examples, but also the lab at DC. It's thelab.dc.gov. If you look at them, they have some great examples on their GitHub as well of, again, real-life experiments. And they're not perfect, right? That's the thing about field experiments, is that they're never perfect. And so it's the best attempts thereof you can find there.
Does anyone else have any other questions or comments? Well, we might just close by saying just very grateful that you're in Toronto, and hopefully you're going to be running lots of experiments here and making things much better here, Kevin. And thanks very much once again for your presentation, both of you presenting last year and now again this year. Really appreciate your time, Jake and Kevin. Thank you very much.
Thanks for having us. This is such a great conference.
Yeah, thank you so much.